All right, we're going to try something a little different today. I think it'll help us be able to get through a couple more questions on the practice exam. So instead of using the board, I'm going to try to use this dot cam. Also, that way, anything that we do will be recorded. So, you know, if you're going through this practice exam, you want to go back and see how we worked through it in class. That should be kind of all in that video. You can kind of see how we worked through it. So the exam on Wednesday, you'll have standard normal, student T, and the formula sheet. I'll give those to you, all right? You'll, should be 20 questions. I was toying around with making the last one short answer, but as I started thinking about time to make that a short answer, we kind of incorporated a few more questions. And I don't know, I think timing might be a little bit of an issue on this exam. So I want to make sure that, you know, I don't allow that to be the case. So instead of doing a short answer, I'm kind of making that last problem just a multiple choice. And I might be kind and have like a bonus question or something like that. Okay. Any questions from me related to kind of just the logistics of the exam?
How many questions is it?
So it's going to be 20 questions. You know, if you think about it, it's going to be what, just under 5 minutes a question, about 4.5 minutes a question. Some of these, as we even review them today, hopefully we'll see, should be pretty, you know, easy. So some of them shouldn't take you near that long. So you'll have a lot more time on some questions compared to others. I'll try to be here kind of pretty early. So if everyone, you know, the vast majority of the class is here, I might start handing things out a couple minutes early just to kind of make sure that timing is not an issue once again. Okay. I'll have blank paper. So if you want to work on, you can always write on the exam. That's okay as well. Other than that, any other questions from me kind of before we jump into some review here? Okay, so, and I'll try to go over some things at the end that I think are just good in terms of like what to review in terms of the topics. But if there's any specific questions, I'll do something from either A or practice exam A or B, but I worked through all those questions on practice exam A and those YouTube videos. So I'm kind of think it's probably smart if we focus on the questions from B. Are there any specific questions, if anyone has taken a look at those practice exams that you want to start out with? Otherwise, I'll probably pick and choose here. Or even if it's just like a set or like a topic that you'd want to see me cover. Nothing. All right, so I will pick and choose here. I'm gonna go down here. And let's kind of work on this proportion one. So let's get rid of this. Let me zoom in a little bit. Maybe we can see this a little bit better. So I'm going to go like 125. So on question 10, right, we've got this information. This is kind of, you know, I give you these practice exams because the exam will be structured similarly. I might give you some information that you can use for the next couple questions, right? That way you don't have to completely restart every question, right, with brand new kind of information or statistics. So we've got some national media source reports that 36% of families own a dog. You want to test the hypothesis, the proportion of families that own a dog is greater than 36%. Right? So when we're dealing with proportions, those are always going to be somewhere between 0 and 1, right? The highest we could see is every single person owning a dog. That would be, you know, however many people in the US there are divided by the, you know, number of people that own a dog. If they all own a dog, there'd just be 1. But we're often kind of given things in percentages, right? So a percentage of 36, we can think of that's going to be a sample proportion of, and actually, I think I can leave everything up here. This will be a little small, and I'll switch to it. All right, our sample proportion in that case would just be, not sample proportion. This proportion that we're interested in, I should say, is 0.36. So this proportion that we're interested in, that's likely going to end up in that null hypothesis, right? We haven't been given any other information, so it's kind of hard to identify the value here. But we want to know whether or not that proportion is greater than 0.36. So whatever we want to test for, that's in our alternative hypothesis. So we want to know, is this proportion greater than 0.36? So what do? We assume the opposite is true, which is that it's less than or equal to 0.36. So kind of remember, whatever you're wanting to test for, kind of however these questions phrase like what you're trying to find, that's your alternative hypothesis. You're then going to assume the exact opposite is true. So if I want to find it's greater than 0.36, my null is that I assume it's less than or equal to. Okay. Now, I think we were given some information up here to do a confidence interval. I might kind of go back and look at this one after we do this hypothesis testing kind of set of questions. But the information we were given up here was that once we've established our hypothesis, right, we've got a sample proportion of 0.4, and it looks like our sample size was 100 households. Okay. So from here, we're going to answer the next couple questions, and I'll kind of make this a little bit larger. But we're going to want to try to identify critical values, our test statistic, and then our p-value. Okay. So if we've got this as our null and alternative hypothesis, what type of tailed test do we have here? Yeah, so we always base the type of test on the alternative hypothesis. Look at the sign in the alternative hypothesis. Or think about it, the type of tailed test we have is what side of the distribution would the evidence that goes against the null and supports the alternative be on? Well, the only thing that goes against the null or supports the alternative would be on the right side, right? Above 0.36. So we're thinking about, we've got our sample proportions, and they should be normally distributed as long as our sample size is over 30. I'm going to switch colors here too, because I think this black marker's dying on me. And we've assumed that true population proportion, right, that cutoff value is 0.36. Now, we haven't assumed it's exactly equal to that, but we said, you know, if we can reject 0.36 with our sample evidence, we could reject anything below that as well. So we then see a sample proportion of 0.4. So we see something on the right-hand side. So we found evidence that goes against the null, but does it go against it enough? Right. So the next step, I think the question was, what are the critical values? Okay. So what we're going to do, and here this might get kind of goofy, but there we go. Anytime we see a proportion example, we should be thinking standard normal distribution. So if you've ever got a proportion, right, we're thinking we're dealing with that standard normal distribution on the Z tables. For a right-tailed test, right, our critical value is going to be on the right-hand side, and our standard normal distribution is centered around 0. So what do we know has to be true about the sign of our critical values? Positive, right? So remember, think about these critical values. What they really are saying is, if the sample evidence you found translates to a test statistic that tells you that it's more than this many standard deviations above that assumed true value, then you're okay rejecting it. So it's kind of like our threshold number of standard deviations that we're setting. Right? So our kind of, I'm not going to try to trick you on the exam. We're going to always have the same 3 benchmark values, 0.1, 0.05, and 0.01. Okay? When think about then our rejection regions are going to be anything to the right for a right-tailed test. So I know the area that I want in the tails here, right? Those 3 alpha values. I want to find the corresponding Z values. That's all critical values are when we're dealing with the standard normal distribution. There are these threshold kind of Z values that we're going to identify. So we'll go to, let's make sure this is working. If anything also doesn't look good up here, it's kind of hard for me to see it out of the corner of my eye. Let me know, and I'll kind of switch it up. So we're going to say, okay, we'll look at here. Well, first of all, we can rule out A and D right away. We've got this down to a 50-50 shot at this point. Right? So I am then going to go to, I'm going to use kind of the shortcut. I think this is the easiest way to do it. We know the areas that we want in the upper right tail. So we wanted 0.1, 0.05, and 0.01. We can use that student T table to find our standard normal distribution values by doing what? Yeah, someone's pointing down, going all the way down to that very last row, where if we could see a degrees of freedom that was infinite, which in practice we can't, but this row is essentially giving us what the standard normal values would be. Because if we could get an infinite number of, infinite sample size or degrees of freedom, then we would basically, the student T would have become the standard normal distribution, right? We said as the sample size grows, it approaches, it looks more and more like that standard normal. If we ever kind of had an infinite degrees of freedom, we'd end up right back at the standard normal.
For the test, you'll give us the Z.
Yep. Yeah. So I mentioned at the beginning, you'll kind of, the packet you'll have within it will be like a Scantron sheet, Z table, T table, formula sheet. Yep. So we're down here at this last row. I might have to like scroll back up to remind myself that these were the three columns that I wanted, 0.1, 0.05, 0.01. So 0.128, 0.1645, and 2.326, right? So, at this point, for this problem, I can identify the correct answer as B, right? I'm going to write these in here before we switch back. Are there any questions on kind of that process? Now, I could have, and it would have taken me more time, and on an exam, I always kind of want to try to give myself as much time as possible. I could have actually used that standard normal distribution, maybe looked up the first alpha of, 0.01. So it looks like it's in between these two values. So negative 2.32 and negative 2.33. So if I had to round to the second decimal, negative 2.33. Now, if I'm looking at that answer key, well, I'm giving it to you in the third decimal, you would have only found negative 2.33, but between these two, you can identify, oh, well, it's closest to this one. I think it would be easy to, if you had to think about, if I could have found it at the third decimal, what value would it be? It's going to be really close to whatever value you had to round to the second decimal. Now, when I looked it up in the standard normal, I found negative 2.33. Why was that the case? Because the table always gives me the area to the left. So if I just looked up an area of 0.01, well, remember for the right tail test, 0.01 was in this right tail. So the area to the left would have technically been 0.99. So that was really the value I should have been looking up. However, once again, just to kind of save time, if I looked up 0.01 in that lower left tail, I know that the Z value I find is going to be the exact same Z value that would give me 0.01 in the upper right tail. It's just going to be negative. So when I find that negative 2.33, I go, oh, well, it's a right tail test, right? I just looked up this small value of alpha. The table always is thinking about the area in the lower left tail. So it's going to be that same value, but positive. Any questions kind of over anything there with the critical values? Okay with all this? What if something changed or? So, yeah.
So is it a right tail because 0.4 is greater than 0.36?
Not so, kind of. I'll say it slightly different. The real reason why it's a right tail test is because my original hypothesis, right? Evidence that it would have supported the alternative would have been finding a sample proportion on the right-hand side. You can still go through a right-tailed test, even if I saw a sample proportion of, let's say, 0.3. But if I had seen a sample proportion of 0.3, I mean, there's no reason to go through this hypothesis test. I found something that supported the null. I know I'm not going to reject it, right? So there's no real reason to kind of continue if we ever saw evidence on the left. So in all the problems that you'll see, if it's easy to think about, yeah, anytime we have a right-tailed test, you're going to see a sample statistic that's on the right-hand side, right? Those are the only ones that are even worth our time, like working through to see if we should reject or fail to reject. That's why I said I hesitate to say that is the reason, because you technically, and I think we worked through one in class, you can go through one where you find evidence that supports the null. It's just why, right? You already know you're going to reject it. Or sorry, not reject it. You already know you're going to fail to reject it, right? You didn't find evidence to support it. So we've got our three critical values here. Any other questions before we kind of keep moving? So the next step, if we were using the critical value approach, and the next problem asks us to find our test statistic. So first of all, if we're thinking about the value of our test statistic, let's go to our formula sheet. We've got our confidence interval equations here, and then our three test statistic equations right here, okay? So we have to identify what test statistic equation do we need? Well, we're dealing with sample proportions and assumed true proportions. So hopefully, if we look at these three, it's kind of easy to identify, well, here's the test statistic that is dealing with proportions, right? At this point, it's just a matter of plugging our values in. So we think about what we've got here. I'll take this away for a second. Our sample proportion was 0.4. That was the sample evidence we found. The assumed true population proportion was 0.36. And then down here, we're just plugging in 0.36 times 1 minus 0.36 over that sample size of 100. Now remember, this represented in my denominator the standard deviation of my sample proportions. In fact, I've kind of got that over here, right? The standard deviation of my sample proportions is just P times 1 minus P over N, and then take the square root. Now we're dealing with hypothesis testing. We don't have the actual population proportion. We're dealing with the assumed true population, but we've assumed that that's a true value. So, right, that would be the value that we're kind of plugging in there. Okay. So we've got that test statistic equation. Hopefully these test statistic ones, I mean, especially if I gave you a proportion, like hopefully from these three, we've seen enough examples and we're comfortable enough identifying. The only one that has notation for a proportion is this last one down here. Now it's just a matter of plugging my values in. Okay. Any questions about identifying what equation we would need to grab there for our test statistic? So I'll give a little bit more things you can kind of think through as well. You know, if we go back and we think about, okay, if I have drawn this out, I always think, like, if I'm taking this, I draw this out and really prevent myself from making easy mistakes. I saw sample evidence above what I assumed to be true. Remember, all that Z statistic or that test statistic is telling you is how many standard deviations away from that assumed true value that your sample evidence is. So if I see sample evidence that's above my assumed true value, the number of standard deviations away is going to be positive or negative. From above it, it's a positive number of standard deviations, right? I'm adding, right, to, I'm going above it, okay? So right away, if I remember, all that this test statistic is, it still represents a Z value, the number of standard deviations away. Now, not from the true mean, but from the assumed true mean, or here, the assumed true population proportion, right? So I know that it has to be positive. And if I looked at the equation, right, the denominator is a standard deviation, so this will always be positive, right? Variances and standard deviations are always positive. So when I'm looking at the difference between my sample proportion and my assumed true proportion, well, anytime I see a sample proportion above that assumed true value, the numerator will be positive, reflecting that, oh yeah, I'm a certain number of standard deviations above that assumed true value. So if I'm looking at this exam, I'm ruling C out right away. Right? Now, the other three, I can't, you know, I have to actually go through and work out what this is. Oh, I'll do it here just to give us a, instead of a calculator, I can probably work through it a little bit quicker here and you can even see what I'm doing. So we'll go 200%. So all I'm going to do is take what? 0.4 minus 0.36 divided by the square root of 0.36 times 1 minus 0.36 divided by my sample size of 100. So basically just, you know, this is, if you take away the equal sign and add in the symbol for taking the square root, this is really what you're going to have in your calculator, right? Now, to prevent yourself from making mistakes, maybe calculate this ahead of time, right? That standard deviation, just to make the, you know, you don't have to use as many parentheses and things like that. If we go ahead and do that, we get what, 0.833. Okay. Any questions there? I have it written down, you know, with a form of the equation here. But right, this is just a matter of getting this entered into your calculator. And I kind of cheated and used Excel here real quick.
This might be a silly question, but did you make up the 0.4 and the 100, or is that in the test?
So, yeah, sorry, I might have went through that quick, right? When we identified that null alternative, I said there was some information given before, but I was going to come back and work on that confidence interval equation. So notice here, we're told the sample portion found is 0.4 out of 100 households. Yep. I made it up in the sense that I actually did go out and try to find a sample, some survey that had some dog ownership. So this is not completely made up. I have some support for this when I went out and found it. Okay. Any other questions at this point? Now, I don't think there's a question asking this, but let's say I had a question where I then said something like, assume that you found the test statistic was blank. So a lot of times I'll do this. I ask you to calculate a test statistic. Well, the very next question, if I then ask you what levels can you reject at, Well, if you got the test statistic wrong, it's probably going to be that you're going to get the rejection levels wrong as well, right? If you would have come up with negative 0.8 here, you definitely would be, completely different than if you found positive. So maybe I do something like tell you the assumed true value of the test statistic. Now here we can actually use the 0.83, but on the exam, I might do something like say, okay, assume the test statistic you found was, I don't know, 1.54, right? So regardless if you got it right or wrong, you're now all kind of working with the same value for that test statistic. Okay? I might ask you, okay, what's the rejection or decision? What levels can you reject at? Well, if we remember, these corresponded to the 10, 5, and 1% significance levels. So if I'm thinking about 1.53, if I have this drawn out where I've identified my critical values, I can kind of see, if I just plot that test statistic of 1.454. Now this has to be like I would give you this on the problem, right? In practice, you would use the 0.83, the actual test statistic, but on the exam, right, I want to make sure that we don't have cascading errors. So if I'm looking here, what levels can I reject at? Well, using the critical value approach, I think the visual, it's easy to see. I'm in the rejection region at the 10% level. I'm just outside of the rejection region at the 5% level, so I'd fail to reject there. And I'm just outside at the 1% level, so I would fail to reject there as well. Okay. Any questions on that rejection decision? I think, if you, like I said, if you draw this out, the rejection decision is a lot easier with the critical value approach. Now, I could have also went through and said, I'll try to leave this up here. Could have said, okay, look, the test statistic I found, right, was, and I think to line up with the practice exam, the next question after you found the test statistic, and I just wanted to give you an example where if I give you an assumed true test statistic, think about how you could make rejection decisions. If you're using that actual test statistic, and then the next question says, what's the p-value? Okay. Well, the p-value represents the probability you saw the sample statistic you did or anything more extreme. I don't say greater because if it was on the left-tailed test, right, it would actually be less than, right? More extreme, kind of going into the tail. So I'll take my test statistic and think about the area under the curve, but kind of to the right in this case, or more extreme than my test statistic. This represents my p-value. Well, if I'm dealing with this standard normal distribution, how can I find this area? If I have a z-value, how could I find the area to the right of it? Yeah.
Convert that z value to p and then do 1 minus that number.
Yeah, so when you say convert it, right, the actual process of what we're going to do is take this value, look it up on that standard normal table, find the corresponding p-value, right? So when we look up that z-value of 0.833, the table will tell us this area to the left. We want the area to the right, so we're then going to have to subtract it from 1, right? So I think, I know when I wrote this current exam, I probably didn't do it here. Where were we? Here we go. Usually what I would also put in parentheses here, if you have a test statistic that's out to the 3rd decimal, I'd say round it to the nearest second, right? Because I can only look up a z-value to the 2nd decimal. So 0.833 here, I'd look up 0.83, right? Now I have a z-value, so I'm looking up a z-value using the row and the column headings. So if I go down here and look up 0.83, I get 0.7967, right? So the area that I found here was 0.7967. I then said, oh yeah, I have a right-tailed test. I still need to subtract that from 1, right? And this is what, 0.2033. Any questions on kind of that process? So anytime I'm looking up a p-value, I think I might have said this at the end of class Friday. Anytime I'm looking up a p-value, that's where I use the row and column headings, right? I'm looking up my test statistic to find this corresponding probability. Right? I know the z-value. I want a certain area in the tail. Now, one thing I could have remembered is if I'm looking at this was I found a positive test statistic. What do I know right away? That p-value, if it's a one-tailed test, right? What do I automatically know that p-value has to be less than? What would the area to the left and right of 0 be? Yeah, 0.5. It's a symmetric distribution. 0 is the mean of the standard normal distribution. So there's 0.5 to the left and the right of it. Well, if I have a test statistic of 0.83, the area to the right of that has to be smaller than 0.5, right? If this area is 0.5, I want an area smaller than that. Right? So the reason why kind of identifying things like that ahead of time is because then when you're looking at these values, maybe you look that test statistic up in the table and you find 0.7967 and you, okay, that's my answer. Well, if ahead of time you would already looked at a visual and said, oh yeah, I automatically, before I even look at the possible answers, I remember my p-value is going to be less than 0.5 because I found this positive test statistic, right? And I'm looking for the area to the right. Right away, I could cross out A. And then when I actually go and look up my test statistic, and I said, okay, 0.79, oh wait, I must be forgetting something. I crossed that one out. I knew it couldn't be above 0.5. Oh yeah, the table tells me the area to the left. I want the area to the right. I still have to subtract it from 1. So it kind of can prevent you from forgetting to make some of these like last step, right? It can prevent you from making these kind of easy mistakes. Okay. Any questions on that one? Okay. If I had wanted you to kind of make a rejection decision using a p-value, like potentially I give you an assumed true test statistic, and I then ask you, or maybe I give you an assumed true p-value and say, okay, now make your rejection decision, right? Well, we only reject if what? The p-value is less than some threshold. What's the threshold we compare the p-value to? You don't remember at all? Right, whatever type 1 errors we were okay making, that alpha, that was like our cutoff. We said, look, I'm okay making errors 5% of the time, right? Alpha of 0.05. The proportion of type 1 errors I make maybe is 0.05. So if the probability of seeing the sample statistic I did falls below that 0.05, then I'm okay rejecting the null. It becomes so unlikely, it's kind of fallen below this threshold I set that I'm okay rejecting. Right? So this is my rejection decision when I'm using the p-value approach. So if I find a p-value of 0.1, which of our kind of 3 conventional benchmark values, 0.1, 0.05, and 0.01, which of those can I reject that? I mean, can we compare numbers? Right? Give me a little bit here, right? If this is our p-value, is that less than 0.1? Hopefully, I mean, you got to be able to know that 0.2 is not less than 0.1, right? I mean, I feel like this is like an elementary, like we're comparing, like, is this greater than this value, right? If 0.2 is not less than 0.1, then we can't reject, right? Well, if it's not less than 0.1, it can't be less than 0.05. It's definitely not less than 0.01. So at all 3 levels, I would fail to reject, right? At none of those alphas is my p-value ever less than that. I'm not trying to be fussies, but like, help me out a little bit here. Like, we should be able to compare these numbers, right? 0.2 is not going to be less than any of those 3 benchmark values, okay? It wasn't a question on this practice exam. I'm adding some things in here that I think might be good for you to know on the exam, right? And I wrote it, so I probably have somewhat of an idea. Any questions on that? So know this. Know that this is how you can make a rejection decision that should make some of the questions on the exam a lot easier. Okay. We'll work through a confidence interval one down here. Any other questions on that? I'll probably start working through the next kind of set of questions here. Now, we could go back and work through some of the earlier stuff. Because I have some videos out there and we spent probably a little bit more time on some of that, I'm going to choose, unless someone has questions that they, if you really want to go over some of the earlier stuff like uniform distribution questions or kind of just the distribution of sample means, we can do that. But unless there's any opposition, I would probably think that kind of working through these examples where we don't have a known population standard deviation. Actually here, this one we do have a known population standard deviation. I might change this one so that we can kind of work through it a little bit differently. And I also want to show you an example of a two-tailed test. Okay. So unless you don't want to go through more hypothesis testing, someone wants to see some older stuff, we'll probably kind of go through that now. Okay. So this won't line up with the answer key. If you want to, you can kind of work through this one and it'll kind of help you see the differences. But here I've got a question where I've got something that's normally distributed and it's got a known population standard deviation. I'm going to work through one where let's assume we didn't know the population standard deviation and all I had was a sample standard deviation, right? Because I think those are a little bit more tricky, okay? So if you look at the answer key, that's how you would work through it if you had a known population standard deviation. We're going to treat this one in class here as though it's only a sample standard deviation. Now, what's the main difference going to be when we work through confidence intervals and hypothesis testing when I only have the sample variance? The key difference is going to be I now have to use I think I did this last class and this is a different section. If I have a sample mean and a known population variance or a known population standard deviation, or I have proportion examples, this is where we could use our standard normal tables. If I've got a situation where I only have a sample variance or a sample standard deviation, we said now it's not going to be quite standard normally distributed when we convert these into z values because we're dividing by that n-1, right? So our kind of variance of our sample means is going to be a little bit inflated. So we should be using the student t, right? So when you're looking at the answer key, it's going to be grabbing a lot of those values. It's going to be using the standard normal distribution. If it was only a sample variance or a sample standard deviation, we have to use the student t, okay? So I would definitely kind of have that down as you're going into the exam. Anytime you see a sample variance or a sample standard deviation, automatically you should know you're using that student t, okay? So in this one, let's say we had, we found a sample mean of 109 for IQ here. We've got a sample size of 49. We've got, and I said, let's assume that it's only a sample standard deviation to make this one a little bit more interesting. So kind of 14 doesn't really apply here in the sense that we've changed the example, but should you use the student t or standard normal when you're making confidence intervals or conducting hypothesis tests here? Well, if it was in fact, a true population standard deviation, that was where we said we should use that standard normal. Or if we line up with the example that we're now going to work through in class because I've changed it, right? We should be using the student t because that population variance isn't known. All we have is a sample variance. From there, let's think about making a confidence interval, okay? So if I want to construct a 90% confidence interval, I'm going to go to my formula sheet, not here, right here. I've got three equations or three different types of examples that we were building confidence intervals for. One, where I have a sample mean and a known population variance. Notice it reminds me, if you have the known population variance, use that z value, use the standard normal table. If I've got a proportion, it reminds me, hey, use the z table. And then down here, if I have a sample mean, but I only have a sample variance or I only have a sample standard deviation, it reminds me, use that student t distribution, okay? So I could write this out and then just start plugging my values in. Now here, I've got to be a little bit careful on this one because I was only given a sample standard deviation. So when I start plugging this in, notice s squared, so I would have to make sure I square that value of 15, okay? divide by my sample size. I've got my sample mean of 109. The only thing left I have to do is find this t-value, okay? Now, one additional piece of information I needed when I was building confidence intervals, when I only had the sample variance, was what was my degrees of freedom? Now, if you look at the formula sheet, one nice thing is it kind of reminds you here, your degrees of freedom is simply n minus 1, or in our case, 49 minus 1, or we have a degrees of freedom of 48. If we wanted the 90% confidence interval, what's our alpha value going to be? Yeah, 0.1. Alpha is the percent outside of your interval in decimal form. So 90% confidence interval, 10% outside. In decimal form, that would be 0.10 or 0.1, right? And we don't really have to put the 0 in there. So I'm then going to go to my student t-table. I'm going to go up here. Oops. Say, okay, the area I want in the tail. Well, now I've got tails, or I've got kind of two sides of my confidence interval. So remember, we're supposed to be dividing alpha by 2. So alpha over 2 here, 0.1 over 2 is 0.05. Right? I have 0.05 on each side of my confidence interval. So 0.05 is the column I want. I'm then going to go down to my degrees of freedom of 48. So the t-value, or the number of standard deviations away I need to go when I'm building this confidence interval, right? The number of standard deviations away I need to go is 1.677. Okay. And from here, it's a matter of computation, right? Getting this plugged into our calculator, okay. I think it's probably not worth me typing this out in Excel, just for the sake of kind of try to work through a few more problems. But if I'm doing this by hand, I'm probably trying to do this in parts. I always tell people with confidence intervals to avoid mistakes, weird as it is, it actually kind of makes sense to work backwards. So take 15 squared divided by 49, then take the square root of that value, then multiply by 1.677, and then you'll add that value to 109 to get your upper bound. You'll subtract it from 109 to get your lower bound. For the sake of saving time on the exam, if it was me, notice none of these upper and lower bounds are the same value. So once you find one of them, like once you found the upper bound, you should be able to identify kind of the correct answer from that. Yes?
So no matter when we use this equation, we will always divide the alpha by 2.
So when we're building confidence intervals, we're always going to divide alpha by 2, right? In hypothesis testing, it can be a little bit different because there, sometimes we're concerned with only one side of the distribution, in which case we don't divide alpha by 2. Now, when we were concerned with both sides of the distribution, like a two-tailed test, it looks exactly like what we were doing almost, well, not exactly like, but like in terms of finding the values from the table, we're always dividing alpha by 2 for that two-tailed test because we're always going to have kind of areas on either side of these cutoffs that we're setting. That's a good question. Any other questions before we keep moving here? Like I said, I don't even know the answers on there won't line up with what we find here, because I think if we did this for a standard normal, it would look exactly the same, except for that z value would be a little bit different, right? Because it has a variance of 1, where our student t distributions have a variance slightly higher than 1. But if you're looking at the answer key, right, that was the one that was treating it like we had a known population variance. It would look a little bit different, but not much. I mean, in terms of the actual steps that you're going through, very, very similar. All right, let's go to this next one. So we're using all this information still, and we're just being given some additional information, right? So now we want to test for whether or not the average IQ, so this was all sample data from Ball State students and their IQ, is it different than the national average of 105, right? Anytime we see this phrase different than, and we're thinking about hypothesis test, we should automatically be thinking about a two-tailed test. So I want to know, is that true population mean IQ for Ball State students different than or not equal to that national average of 105? If that's what I'm trying to find, I assume the opposite is true, which is that it's exactly equal to that value of 105. Okay. So first of all, if I see that phrase different than, I should automatically be thinking about, I should have a not equal to sign in my alternative hypothesis. the way that maybe you could get confused with these values, well, up here we found a sample mean of 109, and here we want to test whether or not it's different than this value of 105. When you're looking at your null alternative hypothesis, it won't be the value of your sample statistic. So whatever you see for your sample mean or your sample proportion, that is not the value in your null alternative hypothesis. That's the value that you're using as evidence to go either against or to support your null alternative hypothesis. Okay, so we've got a two-tailed test here, not equal to sign. Evidence on either side could go against the null. So if I'm thinking automatically, I mean, here I could, think the next question is, well, what are my critical values? Well, for a two-tailed test, right away, I should be thinking, well, evidence on either side would go against the null. So I need thresholds for being, a certain number of standard deviations away on both sides of this distribution. For any one level of alpha, I should have a pair of critical values. Okay. Now, the thing that's a little bit different with a two-tailed test, so we'll come back to this in a second. The thing that's a little bit different with a two-tailed test, right, is alpha is the total area in my tails. Problem is when I only had one tail, it was the total area in my tail, right? Well, now I have two tails. So alpha is the total area in my tails. So I just said before, it's kind of like confidence intervals, right? We should be dividing alpha by 2. So if we go back, I think when we were building the 90% confidence interval, right? Alpha was 0.1, which would mean kind of alpha over 2 would be 0.05 on each side. We should actually find the exact same value that we did for the critical value at the alpha of, right, 0.1, because 0.1 over 2 is 0.05. We'll find the exact same value we found when we were building confidence intervals at the 90% level. Okay. Now, yeah.
So you're using that alpha of 1 from the previous problem?
I was just using this as an example. I think the actual question wants all three, right? The actual question, we're going to have to look up an alpha of 0.1, then 0.05, and then 0.01. Right? I was just kind of starting out with that first one. Yep. So I drew a pair of critical values for this first alpha. I could then draw another pair, the second, and the third pair for the third. Now, when I look these up, it should just all be in one process though. So if I'm thinking about, I had my degrees of freedom earlier, right? We're using the same information. So our sample size was 49. So our degrees of freedom was n-1, or 49 minus 1 is 48. So we're using this row. Our alpha values were 0.1, 0.05, and 0.01. So this is where I said, cross this out, or maybe when you get this on the exam, cross this out right away. This is just representing the area. It's got a visual up here somewhere in one of the tails. So these don't correspond necessarily to alpha. These just correspond to the areas you want in the tail. Well, for a two-tailed test, the area you actually want in the tail is alpha over 2. So we'll take what? 0.1, 0.05, and 0.01. We'll divide them all by 2. So the values that we want in the tail will be 0.05, 0.025, and what? 0.005. Okay. So 0.05, 0.025, and 0.005. These are the 3 columns that we want to look at. We'll scroll down here to our degrees of freedom of 48. Let me get rid of this real quick. And that would be what? 1.677, 2.011, and 2.682. But they'll be positive and negative, right? We'll have a pair of critical values at every alpha level. So let me see here. I'm going to write these out so I can see them, so we can have them. So what? Positive and negative 1.677, positive and negative 2.011, positive and negative 2.682. Yeah, 682. Okay. So from there, right? Now this one won't line up. I'm guessing, right? These are going to be the values that we would kind of find here. I think this is off to the second decimal. Obviously, when I was making this up, they were the wrong answers. So, right, because the actual problem was treating it as though it was a known population standard deviation. But right away, if we know that we have a two-tailed test, we can kind of cross out answers A and C right away. Okay. I want to make sure that we do some things. We have 5 minutes. So I'm going to hop forward just a little bit. But one thing I want to mention here is on the exam, what I didn't do on these practice exams, but I will do on the actual exam is, let's say you identified the null alternative incorrectly here. Well, you're going to find critical values maybe that aren't correct, right? If you thought it was a one-tailed test, but it was actually a two-tailed test. So on the exam, if I ever ask you to like, what's the null alternative? In the very next problem, I'll say, okay, now forget what you just did. Assume that the null alternative is this. And don't read into any of it. Sometimes the assumption will be what the actual null alternative was. Sometimes it'll be completely the opposite, right? But I do that so I make sure, once again, that we're all starting at the same point.
Will there be a question on there where the second question is actually the number that the first question is, or is actually a number that is in the options of the first question, but it's not actually that answer?
I'm not going to try. I'll say this. I'd have to look and I can look and make sure that I'm not doing something like that. I'm not trying to trick you or throw you off or second guess your answer with that assumed true value that I'm giving you. My intention with those assumed true values is something completely unrelated to the correct answer. It's to get at whatever the next principle is. So yeah, do not read into any of the assumptions I give you. Don't let it reinforce that you think you were correct. Don't let it make you think that you were wrong. You shouldn't read into it at all.
But you won't purposely, so like for question 16, let's say, there's those questions, then let's say 17 says, okay, assume true value is this. And it's one of the options A, B, C, or D for question 16. You're not going to purposely put one of the options for A, B, C, or D as assume true value in 17 if that's not what the actual assumed true value is.
So I'm somewhat limited. So when it comes to the null alternative, I might have to do that because I only have really 3 types of tests. And even if I use 2 values, I've only got a combination of 6, and then some of them wouldn't make any sense based off the sample evidence I give you. So that is possible. Like I said, it could even be the assumption I give you could be the correct answer, right? So it's just that you shouldn't read into it at all, which I know is frustrating, but at the same time, it's more frustrating if you get it wrong and you get the next 3 questions wrong, right? So just don't read into the assumed true value. Most of the time, it won't be that, right? I just wouldn't rule it out for these. If I give you an assumed true null alternative, only because we're limited, right? We only have 3 types of tail tests that we can do. But valid concern. I understand what you're saying. All right, so we found our critical values. One thing that I want to go over kind of quick. Hopefully the test statistic isn't too bad, right? That would just be a matter of we identify from that formula sheet. Here's our test statistic equations. I had a sample mean, so hopefully I can identify it's one of these 2, but I only had a sample variance. Now in practice, that doesn't matter. You could actually identify the wrong test statistic here. And once you plug your values in, I mean, all that changes here is the notation, right? So with these sample mean problems, it's not as crucial. Like as long as you're kind of using one of these, you're going to end up with the correct answer. Now with the confidence intervals, you'd be off because you were also looking up, a t value instead of a z value. So the one that I really want to focus on is, let's say we compute this test statistic and we find that it's negative 2.3. Okay. So we find this test statistic to be negative 2.3 for a 2-tailed test, right? Once I plot that test statistic and I want to think about finding my p-value, right? It's going to be the probability I saw the test statistic I did or anything more extreme. But for a 2-tailed test, remember, I only get to see one sample mean, but it would have been equally as likely for me to see something on the other side of the distribution that also went against the null hypothesis. So whatever area I find in this tail, I have to remember it would have been equally as likely for me to see something on the other side of the distribution. And for a 2-tailed test, that would go against the null. So whatever area I find here, I then need to multiply by 2 to determine what my complete p-value is. Because the definition of the p-value is the probability I saw sample evidence as far away from the assumed true value as I did that goes against the null. Well, now that could be either side of the distribution. Now, on a student t distribution example, I wouldn't give you the value of negative 2.3 because we said we're limited, right? If I'm looking here, I can only look up 6 different t values to find the corresponding value in the tail. So I probably would give you something like negative 2.407. So then you could say, okay, at degrees of freedom of 48, 2.407, the area to the left of that right now, here, if I have a left-tailed test, the student T only gives me positive values, but it's symmetric. So I know that the area to the left of negative 2.407 would be 0.01. So if this area is 0.01, I then multiply that by 2 to get 0.02 as my p-value. Now I can use that to make my rejection decisions. Okay. So I go through other examples from the student T distribution and also the standard normal in those videos from Practice Exam A. I have another section today that I'm doing review with as well. I'm hoping to kind of put together some spliced videos that goes through like every question here on Practice Exam B, not just the ones that we did in class. So look for those to be up on that YouTube page. Also, my office hours today instead of 2:30 to 3:30, more like 3 to 4. So if you're stopping by, that would kind of work. Otherwise, tomorrow I'm pretty available most of the day. So even if my typical office hours of 11 to 1 don't work, send me an email. We can try to set up another time if you're kind of reviewing for the exam. Okay. Other than that, good luck studying, and I will see you guys.